let's continue on. We had started looking at the HR diagrams for classification of stars. Now we said that's actually based on the axes themselves are keeping track of measurements of surface temperature, not core temperature, but surface temperature, which we can measure or determine looking at the spectrum of light coming from the star. And then the luminosity is on the other axis, and we said we can determine that by doing distance measurements and brightness. So those are kind of the earliest, most reliable measurements that were doable, and it became a classification system that has stuck. So this HR diagram classification has been around for a long time now. What we can actually do is, using the HR diagram, we can talk a little bit about stars' development, or what's called stellar evolution. So when a star first collapses from clouds of hydrogen, when a star first forms and begins to fuse, run fusion reactions in the core, the surface temperatures and luminosities for those stars are found along the main sequence. And the difference, the other property here that we can measure for the main sequence, or we can determine, is that moving along the main sequence just moves us along different mass of these stars. Now you might be saying, well, how do we measure mass? That sounds like another property that would be pretty difficult to be able to measure. Turns out that about half the star systems that we look at are actually double stars. So there's not just one star there, there's two stars. Think of Tatooine, I guess. So you've got these multiple stars, two or three stars, well, let's say two stars orbiting each other. What we can do is we can actually follow spectral information and Doppler information for that star system and determine the period of orbital motion and get an estimate as the distance between the stars. So it seems kind of remarkable, but looking at orbital motion for these stars, we can get an idea of how much mass they have. Now again, we can build our database up with the stars that are closest, those that we have the most reliable information for. Once we get an idea of what the distribution of star properties look like on an HR diagram for a set of relatively nearby, easy to measure stars, then our assumption is, hey, all the other stars are going to fall into the same pattern. So once we've determined an HR diagram, then we can start saying any new stars that we discover that are farther away would have to end up along either the main sequence or on one of these other branches that kind of extends out from the main sequence. Now we've said a few times now that the main sequence consists of stars that are in the process of hydrogen-helium fusion. What about these other classifications? And when the hydrogen fuel runs out, the lowest mass stars, just the fusion shuts down, they cool down, that's it, they've run out of fuel. So the lowest mass stars don't have enough gravitational force to generate high enough temperatures to fuse heavier elements beyond helium. So now these lowest mass stars also are running at such low luminosities that a low mass star could have a fuel for hundreds of billions of years, even a trillion years. Now the universe isn't that old, at least the phases of the universe where star formation has taken place. And so in some sense, every low mass star that's formed should still be shining and should still have plenty of fuel left for the well into the future. So these stars here. Now when you get into the middle regions, kind of where the sun is located, these stars do have enough gravitational force, gravitational collapse energy release, that the core heats up and you're able to fuse heavier elements. but probably not very far into the periodic table. So these stars can fuse, say, carbon and nitrogen and oxygen. Now, in that process, when they switch from hydrogen fusion into helium fusion, what happens initially is that the core collapses. The fusion reactions have temporarily shut down, core collapses, and then when the new fusion processes kick in, there's a new energy source. And the outer layers get pushed away from the core. That makes the size of the star much bigger. So what we've got then is, we've got what we're thinking of as being a red giant. So now we have a red giant star. What's happening is, for these red giants, the outer layers have spread out. Now what we can also see from the HR diagram, you know, here is the sun, and let's say far into the future, we're estimating 5 billion years. So our estimates for the sun are these. We estimate a star like the sun should have a lifetime of about 10 billion years, and best measurements of the age of the Earth and other objects in our solar system suggest that the solar system formed probably about 5 billion years ago. So there's probably about 5 billion years of hydrogen fuel left in the sun. Now, this is also, it's pretty amazing. I mean, if you go back 100 years ago, or a little over 100 years ago, no one had any idea how these stars were able to maintain these luminosities over long periods of time. There were no known chemical reactions that could power these stars, and then nuclear fusion and processes were discovered. So once people came to understand nuclear physics and the energy available in nuclear reactions, particularly fusion reactions, that was the first time people were able to realize where all this energy was coming from. How could you have a sustained reaction like that? All right, so when the sun fusion shifts into helium, the outer layers are going to spread out. It's going to become a red giant. Now, for the sun, the luminosity overall will increase a little bit, and that says that the core now, the fusion reactions are more rapid. So the fusion reactions that are taking place are happening at a higher rate, and that's why it's higher luminosity. Now, well, if it's higher luminosity, why did the surface cool down? And that's because it's spread out. So the reason that the star now is decreasing in surface temperature is because the outer layers have spread out. Now we're guessing, again, from looking at other stars and what their properties are, we're guessing that the sun, in this process of shifting, turning into a red giant, that the outer layers would reach out beyond Earth's orbit. Now this would be really cool to watch in, like, say, time-lapse photography, right? So let's go 5 billion years into the future. The sun, we notice, you know, is getting bigger and bigger, and we run through time very rapidly to see this effect, maybe run through a few million years very quickly. The sun gets larger and larger, bigger and bigger in the sky each day. At some point, the sun's so big that it has reached the Earth. It fills the entire sky and completely enveloped. That would be so cool to watch, right? The sun getting bigger. Now at the same time, what's happening with the surface temperature and what's happening with the appearance, and the sun's going from kind of a yellow-white star to more yellow to orange, and eventually to more of a red color as that size of the sun keeps increasing in the sky. There's got to be some science fiction movie that has shown that. I can't think of any offhand that I've ever watched showing that expansion of the outer layers as the star shifts from main sequence classification into red giant. All right, we'll refer back to this quite a bit. It does become a really handy set of classifications to think about. So not only is the HR diagram useful for kind of classification, understanding kind of the evolution of stars, we can also use the HR diagram as a way to determine distance. we said the parallax only works so far. Once you get out beyond thousands of light years, parallax isn't going to be as useful. And remember that the Milky Way galaxy, that's like 100,000 light years. So how can we continue to do distance measurements? And so this problem is saying, all right, we have, this is an example of using the HR diagram as a way to determine distance. And it's saying that we have a star, its brightness is 1 times 10 to the minus 12 watts per square meter, and the peak wavelength is 600 nanometers. Let's ask what kind of, what other properties about this star could we determine from this information? So here we go, distance using HR diagram. Here was the given information. They told us that the peak wavelength is at 600 nanometers. Well, we know how to get the surface temperature from that. So using this Stefan Boltzmann, or the Wien's law, we determined that the surface temperature is 4,830 kelvins. So that's the surface temperature of this star. Now, what they also told us is that the brightness of the star viewed from Earth is 1.0, 10 to the minus 12 watts per square meter. Now, if I know what the brightness of the star is, and if I'm looking at the temperature, the surface temperature, 4,830 kelvins, then what we should be able to do is, let's imagine, for example, that the luminosity on this star is 1 times 10 to the 26 watts. So I'm thinking that was, that is a value that we are going to come up with from looking at our main sequence. So what's at the HR diagram. So what's happening here is they've given us a temperature. So we've got that 4,800 kelvins of temperature. And what we're going to do is come up to here on the HR diagram and say, hey, for a star of 4,800 Kelvin, what are the possible values of luminosity that it could have? And so the luminosity value, and that's where the 1 times 10 to the 26 is coming from. So the idea is, from the surface temperature alone, that comes up to kind of a unique location in the HR diagram. All the stars that are at 4,800 Kelvin surface temperature are pretty much at a luminosity of somewhere around 10 to the 26. So that's using the HR diagram to come up with this value right here. Okay, so we haven't used the brightness yet. It's just the fact that it's a main sequence star and it's at 4,830 Kelvin gives us this luminosity. So what we can do now is we can take our luminosity brightness formula and we can solve for distance. So let's do that. This is distance squared. I can put in the luminosity value that I got from looking at the HR diagram. And then I can divide that through by 4 pi times the brightness that was given. And for that, I ended up with a distance. Now everything here is in standard units. The distance is going to come out in standard units also. 2.8, 10 to the 18th meters. And that converts over into 300 light years. So that's handy. Once we get a set of data on these stars, we can start using that data set to determine what the possible properties of another star might be. They're going to have to follow the kind of the same pattern of properties that we have for the stars that we've observed. All right, so we said that on the HR diagram, we're actually seeing stars at different stages of development. And this is referred to as stellar evolution. And it says that we can't really follow one star. The evolution processes for stars take so long, millions or billions of years to see these changes. But what we can do is, from the HR diagram, we can see that stars are in different stages of their development. So I always have a hard time with calling it stellar evolution. You know, biological evolution is a very different process. It's not like, or Pokemon evolution, I guess, is kind of the same thing. It's not like, you know, biologically it's from one generation to the next that evolution possibly can be. Anyway, so when we do talk about stellar evolution, it's really the development of individual stars, how the stars themselves go through stages. Now this is saying star formation, so it's going through some of this. It's saying star formation, interstellar clouds of hydrogen gas and dust. Now, I always had, you know, I would read these astronomy books when I was a kid, and they would always talk about gas and dust and gas and dust, and I don't ever remember being told what dust was. I know what dust is when I'm, you know, sweeping under the bed or whatever, and I go, oh, this dust has been here. Gas tends to refer to hydrogen and helium, which are the most common elements, and they tend to exist as individual atoms or sometimes H2 molecules. Dust are little tiny clumps of typically other elements that have been fused inside cores of stars, high mass stars. Stars blow themselves up, and so you get these little clumps of atoms of different type. And so what they're saying is that there are these clouds that have gas, and then they have these little clumps of atoms in them, and that's what we end up having. A contraction takes place, forms a star, core begins to heat up. Once we get to about 10 million kelvins, the temperature is high enough that fusion reactions begin. Now they're guessing from mathematical models as to how this would occur. From beginning of collapse until fusion begins, maybe 30 million years. When fusion first kicks in, they have luminosities and surface temperatures where they get categorized as a main sequence, and a star like the Sun would take about 10 billion years of fuel is left. Eventually most of the core is helium. So let's see what happens here. So here's looking inside the star. And I think the cores are actually, the fusion regions are probably a lot smaller than this. But what they're showing is that once the hydrogen fuel runs out inside a star, like the Sun, the outer layers then begin to collapse again, and then the temperature increases. When you have gravitational collapse, it's like a bunch of stuff falling towards the center of this star that releases a lot of energy, a lot of kinetic energy of the molecules. They're going faster and faster as they drop gravitationally towards the surface, towards the center. That sets off helium fusion. Now, once the helium fusion starts, then you're generating all of this energy, and the next shell outside, even though the temperatures there are not high enough for helium fusion, they're high enough for hydrogen fusion. So the models that we run as to what's going on inside these stars is that you get these concentric regions of different sorts of fusion reactions going on. So in this case, we just have two different shells. We have helium in the core, and then there's a region out just outside of that where the hydrogen fusion is now happening. In higher mass stars, you could have iron being formed in the core, maybe silicon fusion is happening outside, or oxygen. You could have several layers of different types of fusion taking place inside the star. Now, this outer layer where the hydrogen fusion begins to occur, that's the region that begins to expand. So in this star, it's that hydrogen fusion in the outer, in the shell just outside the core that begins pushing the outer layers of the star, and the star becomes a red giant. So this is kind of describing this effect. I'm going to move ahead and just look at the diagram. I think everything is right here. So it's saying, let's take a star, kind of like the Sun. Here it is on the main sequence. classified in terms of its properties. And then as it shifts over into helium fusion, then what happens is the luminosity begins to pick up. So luminosity, remember, is on the vertical axis. So luminosity is picking up a little bit at first and then much more rapidly. And then here we are at the red giant stage. And then in terms of surface temperatures, we're going to, the surface is spreading out, and so the surface temperature is dropping off. Now there are these sudden horizontal branches, and that occurs when we have these, kind of the next stage of fusion kicks in. So when you get these hydrogen burning taking place around the helium core fusion, then for a brief period of time you've got this extra energy source, and the outer layer temperature goes up, but then as more expansion takes place, the surface temperature goes down again. So we're expecting for the sun that it will go through these stages into red giant, luminosities will go up, the sun will get much larger, and then at some point those outer layers are going to get pushed entirely off of the sun. So those outer layers will become pretty thin. It's not like it's a thick, dense gas. It's a really, really thin gas. And that outer layer actually will separate from the star. And what will remain is the core. So this is kind of a dashed line. Because what we're really looking at now are not so much the properties of this gas that's becoming more and more spread out, but what are the properties of the remnant core of the star, of the sun, that we have. And the core is still at a pretty high temperature, so it could be shining white, but the luminosity is really low. The core itself is not very big anymore. And there's no active fusion taking place. It's just the leftover really high temperature core that's, over time cooling down. So again, kind of an outline of stellar evolution. We saw on the main sequence, we had those lower mass stars, medium mass stars, higher mass stars. The lowest mass stars, they have lifetimes in the hundreds of billions of years. They undergo hydrogen to helium fusion. They're referred to as red dwarfs, but they're all still here. They have lifetimes much longer than the current lifetime of the universe. And so they're still all around fusing. They'll be fusing well into the future. Medium mass stars, like the sun, maybe tens of billions of years, and they can undergo hydrogen to helium fusion. That's the main sequence part of their lifetime. And then they go into the red giant portion of their lifetime, where they're fusing helium into carbon, oxygen. And that's about as far into the periodic table as fusion will take them. And then what we saw in the diagram just before is eventually the outer layers are expelled, they're pushed away, and we're left with a white dwarf as a remnant. Now, maybe the most interesting stars here are these really high mass stars, and they have lifetimes, maybe a billion years or shorter. Maybe it's only in the hundreds of millions of years. They have relatively short lifetimes. And they go through a main sequence phase. They were up there in the upper left of the HR diagram. These are the blue stars, the bright blue stars with these really high surface temperatures and really high fusion rates. They run through their hydrogen pretty quickly. They move on to carbon, oxygen, silicon, iron. Now, we said fusion all the way up to iron releases energy. But when you begin to fuse beyond iron, those elements don't have as high a nuclear binding energy, and so no more is energy going to be released. So instead of energy being released, what's happening then is that there's no additional energy sources from the core, and we have what's called a core collapse supernova. So the core of these stars collapses. Now, in this process, as the core collapses, a lot of energy is released from that gravitational collapse, and that pushes the outer layers outside. We say we have a supernova explosion. Most of the material of the star gets blasted out into space, and little bits of that become dust. So here is the debris left over from supernovas. Now, after the core, the remaining core that's left in a supernova can become a neutron star or a black hole. Now, for neutron stars, what is a neutron star? The stars that we have up to this point, these high mass stars, there's a bunch of protons and electrons in there. And what we saw in quantum mechanics was this. We said that, what is it that holds stuff, prevents solids from kind of collapsing on themselves? And we said that it's the electrons. If I'm trying to compress something that's solid, what I'm pushing against are the wave functions of the electrons. So if we try and compact electrons into a smaller and smaller space, that requires them to have more and more kinetic energy. So I can't compress an electron without some kind of an energy source to make them more compact. Now, for a white dwarf, that would say that there's an enormous gravity collapsing this leftover core of this star, but there's an electron effect. It's called electron degeneracy that pushes back. Now, in a supernova, there's so much gravitational force squeezing down on this collection of nuclei and electrons that the electrons actually are converted into neutrinos. And the neutrinos fly off. The neutrinos can leave that supernova. Now, along with the electrons leaving, the protons in that reaction convert to neutrons. So we've seen this. We saw this in the particle physics chapter. We saw this in electron capture, beta neutral decays in chapter 41. So this is a particle reaction that takes place during a supernova, and what happens is you get rid of your protons and convert them into neutrons. Now, we saw in that chapter, if you go back to chapter 41, talking about nuclear densities, that if there were a way to remove all of the electrons that are big and bulky and have these wave functions that are all spread out, if you replace that with just a bunch of protons or neutrons, things would compact down significantly. So a star with the mass of the sun, if it were to turn into a neutron star, would only be like 10 kilometers across. It would be, the entire sun as a neutron star would be, it would kind of fit in the city of Oakland pretty easily. So you're taking this object, it's just absolutely enormous, and compacting it down into an incredibly dense neutron star. Now, if the star is too massive, if it's got a high enough mass, say 5 or 6 or 7 solar masses, it actually, the gravitation can overcome even the neutron degeneracy. So neutrons, it's hard to squeeze a bunch of neutrons because they have to have much, more and more kinetic energy as a result. But in the extreme case, gravitation collapses a neutron star down to a black hole. Now, black hole is kind of this concept. It's an object, but it's the concept of a black hole is once gravity collapses a neutron star down to a point, once the neutron star collapses beyond a certain density, that the surrounding space becomes distorted. Now, this is kind of the idea of curved space-time from general relativity, which we'll talk about a bit. So for a black hole, the space-time becomes so distorted around a black hole, around what's called the event horizon, that you guys know the story with black holes. If you cross the event horizon, there is no path back. So, and it's not because the gravity can't be overcome, I guess. It's because space-time has distorted to the point where there's just no such thing as a trajectory coming back outside of a black hole in the forward in time direction. Now you could go backwards in time, I guess. You could retrace your steps backwards in time to step out of an event horizon. But in the forward time direction, there just aren't any paths leading out. And that's why people say not even light can leave an event horizon. Again, it's not that the gravity is so strong, it's because space has become so distorted because so much mass is located in a really, really, really small region. Okay. All right, so we talked a little bit about stellar evolution and how stars develop. They're going through these different stages. And but let's step back and see what effect is that having on the universe as a whole. So let's write down a universal timeline. Let's put t equals 0 here. Now t equals 0 corresponds to this high temperature, high pressure, high density plasma state that flooded the whole universe, right? The whole universe was in a hot, dense state. So it wasn't that, and this is referred to as the Big Bang. Now, the Big Bang it's not the best description of what this is. It's not like something started at some location and kind of all this material exploded out into space. That's not it. It's that everything went through a high temperature state, and at these extreme high temperatures, electrons and protons, they don't stick together. So it's plasma. You have a bunch of electrons, a bunch of protons, neutrinos, neutrons, so kind of our fundamental particle list. Now at even higher temperatures, you had some of those other higher mass particles that we talked about in the elementary physics chapter, right? Not only are there electrons, but there are muons and taus. Not only are there protons and neutrons, but there are all of these excited states of quarks, heavier states of quarks. Those could have been around too at extremely high temperatures. As expansion takes place, now you're thinking expansion into what? And space itself gets bigger. So there's just a lot more space around now than there used to be. It used to be that space wasn't as spacious as it is now. Each region of space back then has now expanded into a much larger amount of space. So this t equals 0 that we're referred to as kind of the Big Bang. So we've got this plasma of these fundamental particles. There's the photons right there. And then what's happening is a couple 100 million years into this timeline, you're starting to see star formation. Star formation, galaxy formation taking place. Now, we said that the evidence suggests that we are about 13.8 billion years out of that plasma state. So it's been about 13.8 billion years since that early plasma state that the universe was in. Now, the formation of our solar system was about 9.3 billion years into this. So solar system formed about here. This is today. That's the high density, high temperature plasma state at t equals 0. So what's happened all along this timeline? We said within a few 100 million years, stars and galaxies were forming. So that says that there have been generations and generations and generations of specifically high mass stars. So there's been many, many generations of high mass stars that have come and gone because the high mass stars have relatively short lifetimes. So these high mass stars have rapid fusion. They undergo in the core nucleosynthesis. Now that's the fusion reaction generating heavier and heavier elements. And then here is, the short lifetime, and then they blow up. They supernova. And early in the universe, hydrogen and helium are present from the earliest stages, but not much in the way of heavy elements. So elements beyond helium, not really very much. So what has happened over these generations of high mass stars is that the proportion of material in these galaxies that is heavy elements, well, it's gone from about 0 to 1 to 2 to 3 to 4%. So I put those on the timeline. So what's happened is generations of heavy stars come along, they fuse heavy elements, they blow up. You get these regions of galaxies that are becoming enriched in, these little particles of heavy elements. So 1%, 2%. Now somewhere between 2 and 3%, that was the concentration of heavy elements at the time the solar system formed. Now, most of the stuff in the solar system, it's still, if you listed abundance of different elements, hydrogen would still be the most common element in our solar system, and helium. But here on Earth, a heavy element planet, I mean, this planet's not made out of hydrogen and helium. This is made out of a collection of all of these little bits of debris from supernova explosions that are these heavier elements. So, I always feel like we should have a celebration of heavy elements. There should be a holiday. We should have a holiday to celebrate all of the contributions that high mass stars have done for us. So high mass stars, I mean, how selfless have they been? They generated all the elements that made our existence possible, and then they blew themselves up and enabled the formation of a solar system like ours, where now you've got planets that are exclusively made out of the heavy elements. So that have all the physical properties of all these elements. If you look at the periodic table, all those elements are now filled in thanks to the sacrifices of all of these high mass stars, generations and generations of those. So here's kind of an interesting example too. We said that supernovas occur if we have a star, once they have enough mass that the gravitation is able to allow for fusion all the way through iron, and then there's a core collapse that occurs as a result, and when the core collapse occurs, they supernova. There's another type of supernova that occurs in a double star system. And so what we're saying is there have been two stars in this star system. Here is a white dwarf left over from a white dwarf that's left over from one of the stars has already gone through its red giant stage. And then here is another companion star. Now it's going through its red giant stage. But what happens is, as this star goes to the red giant stage, material from this star gets drawn over to its companion star. So little by little, there's a mass transfer that takes place. The star it was already a little heavier to start with, and it went through its development, its evolution in a shorter time period. Now it's drawing material away from its red giant companion. That's enough, possibly, to tip that star, push it past the tipping point, where once it's collected enough additional material, it can undergo a supernova. Now, this is referred to as a type 1A supernova, and it's a really handy observational object for us. And the reason why is when these supernova, they have kind of a characteristic energy versus time profile to them, and they always supernova with the same amount of energy. So these supernovas are always the same brightness. Now those core collapse supernovas that we looked at, those are going to be brighter if it's a higher mass star and not as bright if it's a lower mass star. But since this star started out kind of below the threshold and got pushed over the threshold by little borrowing material from its companion star, these always supernova with the same brightness. And what that means, these are used to do distance measurements to other galaxies. So we can't use something like parallax for that, way too far away. But you can pick out these type 1a supernovas in distant galaxies, billions of light years away, and you can use their brightness to determine distances. And that's how we've made the most distant measurements to these galaxies. All right, so here is kind of a summary of the distance measurement techniques we've used. Parallax works out to maybe hundreds of light years. Beyond that, we can start using the HR diagram. We looked at an example of that. There are certain other stars, what are called variable stars. They have a definite luminosity. We can use those. And then the type 1a supernovas all have about the same luminosity. Now, we use the type 1a supernovas to calibrate what we call redshift. And once we have the, we'll talk about this some more, the cosmological redshift for a galaxy figured out, we can actually use those as a way to determine distances out to galaxies. All right, it's time for us to move on and talk a little bit about general relativity. So, you know, back in Physics 4a, I think we mentioned this, in Physics 4a when we were looking at the laws of motion and formulas that Newton had developed for gravitation and for how motion takes place, we may have mentioned that that actually isn't the most thorough or the most exact description of how forces behave and such. But we say it works really, really well except under extreme circumstances. Now, what we do have as the best description of how space and time and gravity all are kind of interrelated is general relativity. Now, back in chapter 36, we looked at special relativity. Special relativity introduced us to the idea that the three components of space and the fourth component, I guess, of time, you could take those four dimensions and combine them all together into one mathematical structure. General relativity picks up on that and introduces the idea of space curvature. So it says that in general, you know, the geometry that you've learned in your math classes your whole life, things like the Pythagorean theorem, they only work in what's considered a Euclidean geometry. Geometries can be more complicated than just something that would follow Pythagorean's theorem. So we'll take a look at that. Now, general relativity is based on this principle of equivalence that Einstein came up with. And what Einstein's principle of equivalence was is that, well, if you think back to Physics 4a, remember how gravitational fields had units of acceleration. And to some extent, you can't really tell the difference between standing in a gravitational field versus undergoing an acceleration. And Einstein used that as kind of a jumping off point to develop the mathematics of general relativity. So here it is. This is, here's a person standing in that elevator, and when they're standing in that elevator, if I'm standing in an elevator that's at rest on the surface of the planet, I am experiencing the gravitational field of the planet. But if I were in an elevator that was accelerating through space, that would feel exactly the same. I can't tell the difference between the effects of a gravitational field or the effects of acceleration. So if I'm standing on an elevator, if I'm in an elevator, standing on the surface of the planet and I drop something, it accelerates at some rate towards the floor. That would also happen if I were in a spaceship that looked like an elevator, accelerating through space. Not a constant velocity, but acceleration. So one of the predictions that Einstein made from this was, Einstein said, look, if I'm in an elevator and I shine a light across, the assumption has always been, so the picture on the left is wrong. The assumption has always been that the light just travels straight across. But if I'm accelerating, what would happen is as this accelerates and the light's moving straight through, within my reference frame, within the elevator itself, it's going to look like the light has curved. So Einstein said this isn't really what happens in a gravitational field. In a gravitational field, light actually will be deflected. So not only do objects with mass interact gravitationally, but also objects with no mass. Photons also interact gravitationally. They feel gravitational effects. And this was one of the first predictions, and this is supposedly the prediction that made Einstein famous, was that within a few years from this prediction from general relativity, there was a solar eclipse taking place. Now, during a solar eclipse, it can be that some of the brighter stars are going to be visible. So during a solar eclipse, you can actually see stars in the sky. And starlight from those stars are going to travel close enough if I'm looking at where, the sun's in the sky but the moon's blocking it. And so when I look at stars in that region of the sky where the sun is, starlight is going to travel past the sun, and the sun's got a large enough gravitational field that calculations show that should be observable. There should be an observable effect where the position of the star appears to be shifted when it's actually an effect of curved path of light. And so Einstein predicted this, and some astronomers went and made the observations, and the observations confirmed, or appeared to confirm, there's some contention there as to whether that was really confirming or whether the astronomers wanted to be part of this excitement too. Anyway, the astronomers published saying, yes, we've confirmed predictions from general relativity. Here's another example of that curvature of light. Here's an image of some galaxy, and it's actually, we're getting 5 images, and that's because of the way the light is passing around that galaxy. Now, it's a quasar, it's a certain type of very active galaxy that's generating a lot of light. It's got a supermassive black hole at the core. Anyway, the light gets curved, and so from Earth, we end up with multiple images. It's possible to get multiple images of the same object. So, what does this curvature of space mean? Now, we had mentioned that, you're all familiar with geometry, Pythagorean's theorem. That's kind of how space is set up. But if we had curved space, now three-dimensional curved space is hard to visualize, but we can visualize two-dimensional curved space. So if we take this down to 2 dimensions, let's say that we have, here's a sphere, and if I wanted to, let's say I go down to the tile shop and I find these nice square tiles, and I go, that's a really nice tile pattern. I think I'll cover the whole Earth with that set of tiles. So I come back and I start tiling these, and I put them down on the surface of the Earth. And what I find is, when I start lining up my tiles, which I'm expecting will just be parallel off to the horizon, they don't fit. So as I move, let's say we start at the equator and we start tiling in some direction, those tiles, I have to start cutting little parts of the tile out so that these squares will fit. Now, the equator is just a location for convenience. I could start anywhere on this spherical surface. And anywhere I start with two parallel lines, eventually those lines begin to converge. Now, what they've got mapped out here is, here's an extreme example. Let's say that we map out a triangle within a two-dimensional curved space. So remember, there is no third dimension here. We're imagining that the surface of the Earth is all there is. And so some two-dimensional surveyors get out, measure that straight line, measure this straight line, measure this, they get out their protractors. There's three angles of 90 degrees. That doesn't sound like the familiar geometry. Okay, so curvature of space allows for the possibility, this is referred to as positive curvature. Curvature of space, if it were positively curved, would mean that if you went far enough in any direction, you'd end up back where you started. So I go off in that direction, or that direction, or that direction, or whatever. Now that's hard to imagine three-dimensionally, but that's what's happening on this two-dimensional surface, right? If I start here, for example, and I head far enough in any direction, what happens? And I loop and come right back to where I started. So if you imagine a three-dimensional version of that, that's what space would look like. Now, this is referred to as positive curvature, and it actually gives us a finite amount of space. So the surface area of a sphere, that's a finite number. It doesn't just extend forever. There's no edge. It wraps back around on itself. Einstein liked this idea. What it would do is it would give you a universe that was finite in volume. So once you had gone everywhere and mapped out all the galaxies, you'd be able to publish your book and go, that's it. That's the atlas. We did the whole universe. Here are all the galaxies. Kind of like with the surface of the Earth, right? Once people had mapped all locations and fit all the pieces together, done, the atlas is complete. So Einstein kind of liked the idea that the universe would be finite and have kind of this very interesting positive curvature to it. Now there's another type of curvature that's possible, and that's negative curvature. And for some reason, this is not it. So this says this two-dimensional space has negative curvature. I don't think so. I'm not sure what they're referring to here. This looks like we're still in positive curvature. What it does look like, this diagram is, so I'm gonna cross off the negative stuff. What this does show us is that if we start, let's say that we're on the surface of the Earth, how could we determine if it has positive curvature? How could we determine if it has negative curvature? How could we determine if the surface is Euclidean? And one way we could do that, we could do the tile thing, right? We could get the tiles and set them out. Another thing we could do is we could pick a point to start with. Any location will do. It's a sphere. And then start measuring out distances and then draw circles at that distance and then come out another distance and draw circles. Now, we know from familiar geometry that if we are in Euclidean space, then this statement holds. In fact, that's an example of what we call differential calculus. It turns out that geometry, all of geometry, can be expressed in terms of calculus statements. So there's differential calculus, and what that allows us to do is to state mathematically what the curvature properties are for that particular space. Now, we can start from this and derive all of the familiar geometric formulas that we have. So one, for example, would be the circumference of a circle is 2 pi r. So that would come from starting with the assumptions from Euclidean geometry. Well, in positive curvature, if we started at some location in the Earth and we measured out a couple hundred, 100 miles at a time, or 100 kilometers, and then drew circles, and then we drew a circle here, what we would be finding is that the circumference is less than 2 pi r. Think about that. If you start at some location on a sphere, and you come out some distance and you measure a circle, those circles are not increasing at 2 pi r. They're increasing at a smaller rate, and once you get far enough out, the circles actually start getting smaller. So that would, if you were doing that kind of surveying, and that's what surveyors have done on the surface of the Earth, you find, oh, it's a curved space. It doesn't follow the rules for Euclidean geometry. Now, negative curvature would be kind of the opposite. A negative curvature would say, as you go out and measure those circles, they just keep getting bigger and bigger. Now, positive curvature says that there's a finite amount of space. A negative curvature would suggest, or it would be the case, that space would be infinite. There's no way to terminate that. It just turns out that there's more and more space as you head out. Now, general relativity makes the prediction that positive curvature, when I've got these backwards, so positive curvature, oh no, comes from high density. So it goes like this. Positive curvature comes from high density, and negative curvature comes from low density. And critical density is a term that we use to represent Euclidean space. So general relativity says if there's just the right amount of material in the universe, that space will have this geometry to it. So again, I think we're probably coming up to where we need to take a break on this. Let me check real quick. Yeah, this is a good place to stop. So anyway, again, a correction here right at the end. High density, if we have a lot of stuff, that tends to draw the space-time together and it becomes closed. Low density would be negative curvature.